Good afternoon, folks. This is Mike coming back at you with yet another video on college algebra. In this video, we are going to continue our discussion of matrices and talk about something known as the determinant. So every square matrix, every n by n matrix has a real number associated with it. This is one particular way in which a real number is associated with an n by n matrix. There's other ways that there are real numbers associated with the same matrix, but we focus on this one. The determinant of an n by n matrix A, which we denote by the absolute value of A, that's how this textbook has it noted, or if you read other textbooks, you might see DETA. Either way, we're talking about the determinant of an n by n matrix A. It is written by enclosing the elements of the square matrix into vertical bars. So here's an example of a 3 by 3 matrix. The determinant of this matrix, A, or absolute value of A, is all the elements in the same order, in the same place. We just replace the square brackets here with two large vertical bars. Now, how do we find determinants of 2 by 2 and 3 by 3 matrices? Well, a 2 by 2 matrix is very easy, very straightforward. If you have a 2 by 2 matrix, entries A, B, C, D, then its determinant is AD minus BC. So just as a couple of quick samples here, the determinant of this matrix here, if we look at this as A, determinant of A, 2 times 3 minus 5 times 6, which is 6 minus 30, or negative 24. This matrix here, 4 times 3 minus 6 times 2, which is 12 minus 12, or 0. So very easy to find the determinant of a 2 by 2 matrix. The determinant of a 3 by 3 matrix is admittedly a bit more complicated. There's more involved to it. So here we have this 3 by 3 matrix, entries A, B, C, D, E, F, G, H, and I. The determinant of A is going to be the entry in first row, first column, times the determinant of this 2 by 2 matrix, E, F, H, I. Then minus the entry in first row, second column, times the determinant of this 2 by 2 matrix, D, F, G, I, plus C, entry in first row, third column, times the determinant of this resulting matrix, D, E, G, and H. Now, let me provide some alternate terminology here for these matrices and just sort of what they are. Here we have E, F, H, I, and I'm going to multiply the determinant of this matrix by A. Note that in my 3 by 3 matrix, if I remove the row and the column that contains that element A, so if I were to do this right here, I would be left with that same 2 by 2 matrix. I would be left with E, F, H, I. Here I have minus B times D, F, G, I. If I were to remove the row and column that contained that element B, then I would be left with D, F, G, I, which is exactly that 2 by 2 matrix that I have there. And then I have plus C times the determinant of D, E, G, H. If I removed the row and column that contain the element C, I would be left with D, E, G, H. I'd be left with that 2 by 2 matrix. So what I'm doing here is I'm taking an element and I'm multiplying it by the 2 by 2, or by the determinant of the 2 by 2 matrix that we obtain as a result of removing the row and column that contains that element out front. There's a special word, special term for this resulting 2 by 2 matrix that we get. This matrix here, this is called the minor of A. It's called the minor of A. This matrix right here, D, F, G, I, that's the minor of B. And this matrix right here, D, E, G, H, that's the minor of C. So what we're doing is we're taking an element of the matrix and we're multiplying it by the determinant of its minor. And then we're either adding or subtracting those products. But don't worry so much with thinking about it in terms of the minor if you don't want to. If you find that easier, by all means, stick with it. Go for it. But in terms of an actual formula, we know now how to find the determinants of these 2 by 2 matrices. So it's A times EI minus FH minus B times DI minus FG plus C times DH minus EG. And then if we multiply numbers in, multiply signs in as well, we have AEI plus BFG plus CDH minus AFH minus BDI minus CEG. So, yes, ugly thing that we have to do here, definitely not the prettiest, but the fact of the matter is it does work. So let's find some determinants of some 3 by 3 matrices. First up, A here. I'm going to take 1 because that was my A, and then I'm going to multiply that by the determinant of the minor of that element. I'm going to multiply it by the determinant of this resulting 2 by 2 matrix because we're crossing out the row and column that contain that 1. So 1 times the determinant of 2 to negative 1, 5. Now it's minus B, this element, times the determinant of the matrix I get as a result of crossing out the row and column that contain that element. And the 2 by 2 matrix we get left over is negative 3, 2, 0, and 5. And then plus C, 4, times the determinant of the 2 by 2 matrix we get as a result of crossing out the row and column with that 4, giving me negative 3, 2, 0, and negative 1. All right, so now let's find some other determinants here. I have 1 times 2 times 5 minus 2 times negative 1 minus 4 times negative 3 times 5, negative 15, minus 2 times 0, plus 4 times negative 3 times negative 1, minus 2 times 0. So this is 1 times a positive 12, a negative 4 times a negative 15 is plus 60, and then plus 4 times 3, and 60, 12, and 12 gives me 84. So there is the determinant of this first matrix. The second matrix, element in first row, first column, times the determinant of its minor matrix. 0, 0, 49, negative 66. Minus B, entry in first row, second column, times determinant of the minor of that element. Cross out that row and column. You're going to be left with 0, 0, 37, and negative 66. Minus 11. Plus our C value, but it's minus 11, so it's plus a negative 11 times. Mentally cross out row and column containing that negative 11, and you have 0, 0, 37, and 49. Well, if you do these determinants of these 2 by 2 matrices, 0 times anything is 0. 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 You can probably see the pattern that's going to happen here. We get 0 and 0. This whole big thing is just going to be 0. So I purposely gave you a matrix such as this. If you have a row that is all zeros in your matrix, then the determinant of your matrix is going to be a big fat 0. So these are our 2 sample problems with finding the determinants of some 3 by 3 matrices. 2 by 2 matrices, very simple, don't need to do much practice work with that. Now, in the previous video, we had talked about the inverse matrix, what it is, how do we verify that a matrix is an inverse of some other given matrix. But we also said that we would talk about when we know that we have it. How do we know when a matrix A has an inverse matrix? Well, what dictates whether or not we have an inverse matrix is actually the determinant of the given matrix. And it's actually very simple to figure out whether or not the matrix A has an inverse. An n by n matrix A is said to be invertible. That is, it has an inverse matrix if and only if the determinant of A is not equal to 0. If you want to know if your given matrix, your given n by n matrix A has an inverse, all you have to do is find the determinant of that given matrix. If its determinant is not 0, then you know that the matrix has an inverse, and you can go ahead and find it. So here, just one more quick sample problem. I'm actually going to let you guys try this one on your own. Figure out, is this matrix invertible? Not that you have to find the inverse matrix if there is one, but just figure out, does this matrix have an inverse? Use this fact that we just said here and calculate the determinant of this matrix. If it's not 0, yes, it is invertible. If the determinant is equal to 0, then no, not invertible. So pause the video. Once you think you have the answer, press play, and we will see if you are correct. All right, let's see if you came up with the correct answer. Hopefully when you found your determinant of your given matrix, you had 5 times the determinant of the 2 by 2 matrix 1, 3, 7, negative 4, plus 2 times the determinant of the matrix 1, 3, 0, negative 4. This is a plus 2 because typically we'd have minus, but our value here is negative. So minus that minus becomes plus. And then we have minus 2 times the determinant of the 2 by 2 matrix 1, 1, 0, 7. Do those calculations, you should have come down to negative 147. That is clearly not 0, so the answer is yes. This matrix is invertible. It does have an inverse. So guys, we're going to stop there for now. In the next video, we will continue and we will see how we can use determinants to actually help us solve systems of 2 or 3 linear equations in 2 or 3 variables. So if you guys have any questions or comments, please be sure to reach out to me. Emails, texts, paper airplanes, codified messages, whatever. Until the next video, take it easy, guys.